Up to now, we have restricted our regularization function Rw as follow 1 over 2 eta W normed square. Okay, so then what will happen when we use more general R function? So to understand the behavior with general R function, we need to understand Bregman divergence and mirror descent approach. Okay, so the Bregman divergence associated to function f is this. So especially when we use convex function f, this Bregman divergence imply the difference between this convex function f and the tangent approximation. So this is basically when this is y point and this is x point, the tangent line equation is inner product between f y and x minus y. This tangent line, we know that from the convexity of f, we know that this is below function fx minus fy. Of course, fx minus fy. Right. So, using this fact, we know that fx minus fy minus inner product between gradient fy and x minus y is greater than or equal to 0. In this graph, this gap is the Bregman divergence, and which always positive. But note that the Bregman divergence is not distance. Usually the fxy is not equal to f. Okay? So when you change x and y position, then we cannot guarantee equality. I mean, the Bregman divergence is not symmetric. Okay? But of course there is some case the equality hold, but usually with general function f, the Bregman divergence does not have symmetric property. Right. So why I introduce the Bregman divergence? The Bregman divergence with respect to the additional regularization function R has very important meaning in online mirror descent and the online convex optimization problem. And the Bregman divergence of 1 over 2 normed square, this is very interesting and very important. So what is this? 1 over 2 x normed square minus 1 over 2 y normed square minus inner product, what is gradient of y normed square 1 over 2, that is just y. So the inner product between y and x minus y. This is equal to 1 over 2 x normed square plus 1 over 2 y normed square minus inner product between y and x. This is equal to 1 over 2 x minus y normed square. Okay. So the Bregman divergence of normed square function is just distance, Euclidean distance. Right. But when we replace this normed square to more general convex function, such very beautiful property does not hold anymore. Bregman divergence is not distance. It has not symmetric property. Okay. Right. And we also need to know mirror map. So what is mirror map? essentially we have original space x with a function pi, usually convex function pi, and its gradient. We can make a mapping from original space to its dual space, okay, like this gradient. Okay, so this map is called mirror map. Why we use mirror map here? Mirror descent algorithm basically do not update the value from the parameter space, but from the dual space. Okay, so gradient descent, original gradient descent rule. In the previous case, we update wt plus 1, that is equal to wt minus step size gradient f wt was gradient descent. Okay, so this was ft. This was gradient descent, and this basically update the parameter in the parameter space, which directly move the parameter vector or hypothesis vector w in the hypothesis space. But the mirror map, we first map the point using mirror map and move like this. Okay, we update our gradient descent rule not in the original space but in the dual space. Okay, so this is the mirror map update rule, or called mirror descent approach. So more precisely, xt first map to gradient of xt, and then compute gradient of pi xt minus eta gradient of fxt, and then find yt plus 1 such that gradient of pi yt plus 1 is equal to gradient of pi xt minus eta gradient fxt. So basically this operation is inverse operation. So we have mirror mapping, and also we have inverse mirror mapping, which mapping from the dual space to the original space. And again, it is possible yt plus 1 is outside of our constraint set, so we have to learn some projection operation. In this case, instead of simple Euclidean projection mapping, we use Bregman divergence projection mapping. So we find the point x among our constraint having the least distance, smallest distance, or smallest Bregman divergence when we compute d pi x and yt plus 1. Okay, that is called mirror descent. And why we have to study mirror descent? Consider you have regularization function w, Rw is equal to 1 over eta pi w. Okay, imagine we have a regularization function Rw is equal to 1 over eta times some convex function pi w. And let's imagine we don't have any constraint on hypothesis class. Okay, then we basically have to optimize for the wt plus 1 we have to optimize from I1 to t gradient of ft wt and w plus rw. Why? Which comes from this f tilde operation, f tilde conversion. Okay, since max summation t1 to capital T f t wt minus ftu is upper-bounded by max summation t1 to capital T f tilde t wt minus f tilde tu, when we can upper bound the regret of f tilde, this upper bound naturally upper bound the regret of our original function f. And here f tilde, from the definition, this is inner product between fi, wi, and w. Okay, so we can write down this. Okay, so this is argmin, right? And the argmin is the point gradient of r wt plus 1 is equal to summation minus eta times summation from I1 to t gradient of f t w t, which basically gradient of r w t is equal to t plus 1 is equal to gradient of r w t minus eta gradient of ft wt. Okay, this is mirror descent without constraint. Okay, so when we use L2 norm regularization term, then the follow the reader rule becomes gradient descent or O-line gradient descent. When we change the regularization function to 1 over eta times some convex function pi w, then the updated rule becomes O-line mirror descent. Okay, so when we can analyze the performance of O-line mirror descent rule, we can analyze very general version of follow the reader rule with regularization for that algorithm. Okay, so the O-line mirror descent formally again we start with running parameter eta and 0 starting point. At each time we predict wt and receive the loss value and the gradient, and update our parameter using mirror descent rule. And if the value is outside of our parameter constraint, then we project the point to the inside of our hypothesis class using Bregman Divergence. That is O-line mirror descent. And this is the performance. O-line mirror descent has this regret upper bound. And this regret upper bound, when you look at this, there are two terms. The first term is the Bregman divergence between the optimal fixed policy u and our initial point W1, which basically 0 point, plus 1 over eta times Bregman divergence between the previous time slot and the mirror descent updated. So this kind of tell us kind of stability of our algorithm. Every update, every mirror descent update change how much of Bregman divergence. And this term tells us the diameter of our hypothesis space. Of course, when we change the regularization function R, when R is 1 over eta pi, so when you change pi function, this diameter and this stability term will change as well. Okay, this is very important. Indeed, there is some trade-off. When you control pi, either this increase and this decrease, or this decrease, this increase. In general, there is some trade-off relationship between this diameter and the stability term. Okay. So depend on which problem you attack, we have to well control the regularization function so that our regret can be minimized. We will study some catalog of pi function and their applications. We will see very interesting theoretical result of online optimization problems. By changing the pi function, we can observe very different regret values, regret functions.